Hello and 안녕하세요, everyone. Welcome to 77th session of Pulse Media Tea Time Talk. My name is Sang-Lee, one of the organizers of the Pulse Media Tea Time Talk and part of the Interpol Young Academy. And as you have guessed from my introduction, and also if you have seen my advert that I sent out earlier, that this month is Korean Researcher Special. And to celebrate that, we have two awesome young early career researchers from South Korea. So without any delay, I would like to introduce our first speaker, Taehoon. So Taehoon is, yeah, you can set up your slide while I'm introduce you. So Taehoon is a postdoctoral researcher at Center for Water Cycle Research of Korea Institute of Science and Technology, or in short, KIST, in South Korea. His research focuses on hydrogeological fluid dynamics and numerical modeling, specifically addressing the behavior of environmentally hazardous materials. A key strength of his work lies in developing a site-tailored evaluation framework by integrating data-driven analysis with numerical simulations. Taehoon's goal is to extend this framework to address a broader range of emerging contaminants. Today, he will be talking about evaluation of DNAPL contamination across porous media and fractured media using integrated numerical modeling. Taehoon, floor is yours.
Okay, let's get started. Is it okay?
Yeah, everything looks good. Yeah.
Okay, so hi everyone. Thanks for joining today. My name is Taehoon Kim, as introduced. So I'm a postdoctoral researcher at KIST, Korea Institute of Science and Technology, and Water Cycle Research Center. So today I'm going to talk about a way to make the integrated numerical modeling to quantitatively evaluate the DNAPL contaminations, especially across both porous and pressure media. So let's get started. But first, so here's a little bit more about my research background. So I joined KISS in November 2024 after graduation. And my research approach combines the numerical simulation with data analysis to understand how the contaminants move or transport through the porous media, in the subsurface, like the porous media and pressure networks. I work with various contaminants according to the project. So currently I'm working on heavy metals or PFAS a little bit, but during my PhD, I spent a lot of time on NAPL or volatile organic contaminants. And today's presentation is actually based on my PhD research, the DNAPL prediction model. Okay, so let's get into it. And this is part one, integrated DNAPL model. So what exactly is DNAPL? It stands for dense non-aqueous phase liquid. So basically it's an heavy oil contaminant from human activities, and it has high density and limited solubility in water. So examples contains hydrocarbons, chlorinated solvents like TC and PC, or some pesticides. When these are released into the subsurface, they migrate downward toward the top of the bedrock, and when they reach the pressure rock, they can migrate all the way down through the permeable fracture below. So these two media are fundamentally different in their geological structures or characteristics. And to keep it simple, the pulse media has continuous force and permeability. So we need a continuum model approach for a numerical simulation. However, in pressure media has a discrete force and permeability structures. So we need to represent it using a discrete pressure network or DFM model. This is the tricky part. As I said, the continuum model and DFM model are fundamentally different. They have different governing equations, and they use different grid structures or different way of defining properties. So traditionally, it has been really hard to combine these two into a single model. To address this, we apply the concept called upscale discrete fraction method, which is developed by Sweeney and his colleagues in Los Alamos National Laboratory in USA. So the idea is quite simple. Pulse media is already a continuum form, but DFM model is a discrete fraction form. So we convert it into the equivalent continuum properties first. Then when those two pulse media becomes a continuum framework, then we can integrate it. So this is how we built the integrated network prediction model. But here's some more details about the how integration actually works. So first we have pulse media, which is already in a continuum scale, so governed by a Darcy's law, and use macroscopic properties like porosity and permeabilities. And we also have a pressure rock at bottom left, which is in the DFM form, governed by Cuban law and use microscopic properties like strike, dip, or aperture size. So to connect these two, we use the upscale discrete fraction network algorithm, and the algorithm is worked in these basic 3 steps below. First, octree-based mesh refinement. So instead of using uniform grid law, the algorithm generates the really fine meshes, especially around the pressure first, while leaving the solid matrix area coarse. And second, derivation of equivalent properties. So we take these grid structure informations like strike depth or aperture size and mathematically convert this into the effective permeability tensor, which is right here. And then the third, continuum property mapping. We assign this permeability tensor and equivalent porosity back onto the refined mesh, which made in these steps. So the process is like is in this video. So like this. So after all the upscaling process is done, the pressure rock with the DFM form is completely translated into the continuum scale like this. So when the upper pulse media and pressure rock now becomes a continuum scale, then we can integrate them. And so we'd like to make this model more realistic. So we utilize the actual field data from a test site in Korea. The model built in 3 stages, integrating data from geophysical logging, geophysical surveys, bore loggings, monitoring, and samplings for both pulse media and pressure rocks. So this captures the heterogeneity in the site. And after the integrated model built, we perform the numerical simulation over 40 years. We assume the hypothetical DNAPL release at the depth of 15 meters. And during the first 10 years, as you can see, the DNAPL plume are migrate downwards, driven by gravity. And here you can see the heterogeneity in porosity and permeability. Also, there are some zone of delaying migration zone, so near the water table because of the buoyancy or viscosity resistance of the groundwater. And after approximately 10 years, the DNAPL plumes reach the top of the pressure rock, and it can no longer migrate downward. But over time, the DNAPL plume can frequently migrate through the permeable pressure below, and part of the DNAPL plume remains in the porous media at a low saturation as a form of residual trapping. And also, we can extract some spatiotemporal information about the DNAPL plume with this integrated model. So these three figures represent the different zone in the subsurface. The first one is unconsolidated soil, and second one is weathered rock. Both these two media comprise a porous media, and another one is the pressure rock. And here you can see the arrows, which means the movement of the center of mass of the DNAPL plume. Also, you can see the blue circle, which represent the horizontal variance of the DNAPL plume. Basically, the horizontal spread, how spread out the plume is. So, with this integrated model, we can track the DNAPL plumes, not only where the DNAPL goes, but also how spread or evolves over decades. So that was a part one, building and running the integrated DNAPL prediction model. But here's the thing. With the single deterministic predictions, we cannot be so confidential or confident with the predictions because they have many uncertainties in the subsurface, like heterogeneity and parameter variability or some other complexities. So properly handle this, we need a probabilistic approach, not a single prediction, but thousands of scenarios to cover full ranges of possibility. So in part two, I will show you how we developed the surrogate model to make this probabilistic prediction much more efficiently. And we do sensitivity analysis to figure out which parameters drive the DNAPL risk at the most. So the problem with the numerical model is that running one simulation requires a lot of computational times and resources. To conduct a probabilistic analysis, which requests hundreds or thousands of scenarios, it is impractical. So that's where the surrogate model comes in. The idea is simple. We train a surrogate model to run the relationship between inputs and output by running a multiple numerical simulation with different combination of input parameters like this. And in our case, the output is the DNAPL mass in pressure rock, after 40-year simulations. And to train the relationship between the inputs and output, we apply the polynomial Gauss expansion, or PCE, and a random forest surrogate model, which is one of the well-known machine learning algorithms. On the right side, we have model performance of both surrogate models. There are comparisons between both surrogate models and original numerical simulation results. So we can see that the surrogate models work well. So that shows the great accuracy. The training data pitch well with the original data, and test data validate reasonably. So from now on, we can use these surrogate models, replacing the numerical simulation results. So we don't have to iteratively conduct the numerical simulation, which is really heavy from now on. Yeah. And you might wonder, why do you choose those two surrogate models? Because they have interpretability in their analysis predictions. So the surrogate model can be classified into three types based on the interpretability: white box, gray box, and black box models. The white box model, like the polynomial Gauss expansions, is fully transparent. So because it is made of the mathematical formula, they have always the analytical solution for the probabilistic predictions. And random forest is a gray box model. So it shows some patterns and some pictures from this, but we can not see the internal logic, full internal logic, because it's so this is why we called it a gray box model. Otherwise, we have black box model, such as neural networks. So we cannot see the internal logic of the models at all, because it is too complicated. And even though if it shows the quite a great quality. And one more thing is, both model can conduct a global sensitivity analysis by its own, and we can also compare these two results for making some robustness of the analysis. If we get the similar results from both two models, then we can confirm that it has some meaning, physical meaning, not the algorithm artifact. So from now, we have our PCE and random forest surrogate models. Then we can conduct a Monte Carlo simulation, which are the large-scale random sampling for along the whole input parameters. These are the results of Monte Carlo simulations for the most important value and most important variables, which is permeability anisotropy, depth of water table, and residual saturation of DNAP pool. The x-axis represents the input parameter range, and the vertical axis represents the predicted value of DNAP pool mass, which reaches the fracture rock. So as we can see first, the permeability anisotropy shows a positive trend. And so which represent that as the anisotropy increase, the more the nipples are reached to the pressure rod. So similarly, as the depth of water table deepen, the more the nipples can reach to the pressure rod. In contrast, the residual saturation shows a decline trend, which represents that the increase of residual saturations, the more the nipples are trapped within the upper porous media, and then less part of the nipples moves to the pressure rod. And also we can compare the upper part with the bottom part. So one represent the PC predictions, and one representation the random forest predictions. They show the similar trend line, although they have the different patterns because of their inherent difference in their theoretical backgrounds. And following the Monte Carlo simulation, we performed the global sensitivity analysis. So in this figure, we have the magenta bars, which represent the sensitivity indices from the random forest surrogate model predictions. And other two black and gray bars represent the sensitivity indices from the PC surrogate model predictions. As you can see, they show the similar result, which means they show these results are quite robust. This sensitivity analysis is quite robust, so and reliable. And finally, we obtained the quantitatively identified the most important parameters in these scenarios. Again, permeability anisotropy, and depth of water saturation, and the residual saturation. So we can choose the properties that we have to focus on. But here's an issue again. Two of these three parameters are really hard to measure in the real field scale. The permeability anisotropy and residual saturation is hard to measure, but luckily we have the depth of groundwater, which is more relatively easy to measure. So this provides us some practical approach to for risk assessment. We can use the depth of water table as a reference point, and we can evaluate the risk based on the uncertainties of these unknown parameters. So we have three heat map plots. So for each water table depths, and the x-axis represent the residual saturation, and the y-axis represent the permeability anisotropy on log scale. The colors are predicted by a PC model and represent the risk of the nipple which reached the pressure rod as percentages. So there's a progression from the left to the right side. So at 10-meter depths, there are almost a safe area. So there are low risk level of the nipple avoiding to the pressure rod. And at 20 meters, the dangerous risk level categories appears at the upper part. And at 30-meter water table depths, the dangerous zones are expanded, and highly dangerous risk level appears. So the conclusion is quite clear. As the water table depths deepen, the much more region of high levels of risk appears. Okay, so this is the summary of today's presentations, and now I'd like to talk about implications of our study. So first, integrating the force and pressure media environment. This is actually one of the first attempts to model these two environments together for contaminant assessment. Traditionally, the pressure rock was considered too complex to understand, so it was often excluded from the limitation zone. Our approach expand the view. We can now assess contamination behavior across both zones in a unified way. And second, a practical framework for probabilistic analysis. With growing computational power, probabilistic analysis has become essential for handling uncertainties existing in the subsurface. So we developed a versatile framework that can be applied to diverse contamination sites and contamination types. So not just for DNAPU, but potentially other contaminants and sites. And third, the significant expansion of surrogate models. Surrogate modeling is growing rapidly alongside AI development. Advanced methods like QNNs, quantum neural network, or physics-informed neural networks, or neural operators are emerging, so offering even faster and more accurate predictions. So this field has potential for the future. Okay, so that is all for today's my presentation, and thank you for listening. And I'm happy to your questions.
All right. Thank you, Taehoon, for your wonderful talk. And those of you who are watching on YouTube, and if you have any questions, please write your question in the chat, and that will be addressed by Taehoon in a few seconds. If you're writing or thinking of the question, I have some questions to you, Taehoon. It may be a bit dumb question. I'm not an expert in this field, but I wasn't too sure whether you had modeled the DNAPO transport into the rock matrices. Can you comment on how DNAPO trapping in rock matrices and dead-end fractures can, how significant that is in your modeling or in real systems?
So to be honest, there are less effects in the matrix diffusion in our model, because the permeable there are some regions, but firstly, so our aperture size is quite big, which is determined by the image analysis from here. So because aperture size is too big, the permeability is quite huge, like 9.67 and 10 to the minus 7. So it is quite huge. So we thought that diffusion might be negligible in this scenario. And also, but we can apply the diffusion effect where the migration into the matrix, but in this scale, with a very large scale, we cannot find any evidence for the matrix interactions in the pressure rock. So, and also resolution is, but I think the effect is employed, and so it's in the inherent algorithm. So we can consider that, and we considered that, but yeah.
Does it require too much of computational power if you were to take into account the matrix diffusion?
It is okay, but but the thing is, in our case, it is negligible. So
I see.
yeah, the effect was not appeared.
Thank you. And I have more question to you. I know in fractures the flow velocity can be quite high. So I wanna hear from you that if you can take into account any inertia effect in the flow and transport of DNAPO through fractured media in your model.
Okay, so as we consider the actual field data, maybe the model follow the realistic real world, but so but so we have boundaries, and so you can see that there are some accumulation so at the bottom of the model, and this can cause some errors from our intuition. But this is kind of a limitation of our study. But as you said, the migration in the permeable pressure is really fast, so they can migrate very rapidly, even out of the this model domain. But to maintain the iterative, maintain the I'm sorry. So I'd like to maintain the total mass within the domain. So yeah, I intendedly limit the boundaries so they accumulate at the bottom of the domain. So yeah.
I see. Yeah, thank you. I don't think I see any questions in the chat, so we could wait a little bit, but for the sake of time, I think we have to move on. I thank you again, Taehoon, for the wonderful talk. And those of you who have questions but didn't get to ask him, you can leave a comment in the chat. Oh, we have a question that just came up.
Okay.
So Iron Addict 4737, if you can, yes. So he has two questions. First, I was wondering if there was a specific reason for capping the permeability anisotropy ratio at 2.0.
Okay, the parameter range are based on the literature reviews and some kind of our from our intuition. So okay, here. So I decided the boundary of from 0.5 to 2 because in nature we rarely see the permeability anisotropy which reaches the 2 because it means the vertical permeability is higher than horizontal permeability, and in that case are not that much. So I so So I so I limited the upper boundary as a 2. But and also I have to consider the total convergence ability of the models. If I choose the outer values, then the model might be failed or doesn't get reached to the convergence. So yeah, I intend so there are several regions to to consider these boundaries.
And the second question is, since you focused on PM effects, how can we quantitatively assess the specific impact of FR properties on the total dnapple mass?
Okay, this is really good question, I think. So here's the 7 parameters that I consider. So first, before I write the paper and make research for this, I thought some kind of pressure properties can impact sufficiently of the overall migration of dnapple, because when the dnapple migrate rapidly into the deeper structure, then I think the dnapples in the porous media can move quickly into the pressure well. So I thought like that, but after the research, I found that this this is quite negligible. So yes, and to be honest, I should take more variables other than this. But so as I said, there are some limitations to consider the boundaries because of some modeling, some numerical problems. So after all of the consideration, I choose these values. And other thing is that these properties are independent, so they have less impact from each other. So it is really important to when you take the probabilistic predictions or analysis. So I choose these properties because they show less. I found that they show the less impact each other. So yeah, several reasons are here.
Okay, we have to move on. Let's thank Taehoon again. Thank you.
Okay,
So-
thank you for asking.
We'll move on to the second speaker, Hyunjeong. Hyunjeong, if you could open up your slide, that would be great while I'm introducing you. So Hyunjeong is a PhD candidate in Yonsei University in South Korea, conducting research in the field of geologic carbon sequestration. Her work focuses on pore scale and core scale processes, with particular emphasis on multi-phase flow modeling and X-ray CT imaging analysis. Through this research, Hyunjeong aims to contribute to the practical advancement and wider implementation of carbon capture and storage technologies. And today she will be talking about microstructural controls on CO2 mineralization in basalt revealed by multi-scale X-ray CT imaging. Hyunjeong, floor is yours.
Okay, thank you. Can you hear me?
Yes, I can hear you well.
Yeah. Okay. Good morning and good afternoon, everyone. Thank you all for joining me today. I'm Hyunjeong from PhD candidate from Yonsei University, South Korea. Actually, I'm a bit nervous to be speaking in front of such a global audience, but it is truly a great honor to present my research at this press media Tea Time Talks. And today I would like to share our recent findings on CO2 mineralization in basaltic rocks, specifically focusing on how microstructures revealed through multi-scale CT imaging govern mineralization potential. Yeah, so I will start with a brief introduction, followed by materials and method, key results, and conclude with key takeaways. So I believe most of you guys know about CO2 mineralization, and this CO2 mineralization has gained significant attention as a key component of carbon capture and storage to mitigate global warming. And this technology involves injecting CO2 dissolved water into the mafic rocks, like basalt, which are rich in divalent cations. And this triggers the precipitation of carbonate minerals, permanently sequestering CO2 underground in a stable solid form. And the advantages are very clear in much shorter timescales, often within a few years compared to conventional trapping mechanisms and the global abundance of the basaltic formations. In particular, the KIST project in Iceland demonstrated that over 90% of injected water, CO2 was mineralized within just 2 years, proving the immense potential of this method. So here are the critical factors of CO2 mineralization, and X-ray CT imaging has become a vital tool for non-destructively investigating these properties. However, as shown in this literature review, most previous studies relied on low to medium resolution scans. Actually, while some sub 2 micrometers high resolution studies exist, but they were not focused on characterizing basalt for carbon storage. So here are the core problems we face in this field. Most existing studies are just limited to low or mid-resolution imaging, and they are typically based on just single type of basalt. And this lack of resolution and diversity has resulted in an insufficient understanding of the complex characteristic of basalts. And to overcome these limitations, we utilize the synchrotron-based high-resolution CT imaging to uncover the hidden microstructures that were previously invisible. In addition, we performed a comparative analysis by incorporating low-resolution imaging, which is widely used in conventional studies. And we also conducted detailed geochemical analysis to comprehensively characterize the geochemical properties of the basalts. And throughout this approach, our study focuses on 3 primitive objectives. First, we aim to reveal the structural features that are previously unresolved across diverse basaltic lithologies. Second, we will demonstrate exactly how microstructure control the critical factors such as fluid transport and surface area. Finally, we developed a microstructure-informed framework for quantitatively evaluating CO2 mineralization potential. So to achieve these objectives, we compare 2 distinctive basalt types. One is the highly shady basalt from Iceland, the site of the KIST project, and the Jeju basalt from the South Korea. And as you can see, these 2 samples represent very contrasting geological origins, which resulted in distinctive structures and characteristics. And the key method in this research is the use of synchrotron at the Pohang light source in South Korea. And this advanced imaging allowed us to obtain high-resolution 3D data with a voxel size of 1.625 micrometers, which is essential for performing digital rock physics-based analysis on micropore characteristics of basalts. And we also conducted comprehensive geochemical analysis to characterize the geochemical composition of basalt samples by integrating XRD, SEM, and whole rock analysis, etc. Now let's see the results, starting with our observations of microstructures. So this is the highly shady basalt core, and when observing this core visually and through the low resolution CT, we see large vesicles and a relatively homogeneous and smooth matrix. However, high-resolution imaging reveals a completely different world, a complex network of microcracks, micropores, and unique microstructures like nodule, as you can see here. And by capturing these hidden features, we found that the surface area is actually 6.5 times larger than what low-resolution data suggested, despite having nearly identical porosity levels. So yeah, this dramatic surge in surface area is driven by these hidden microstructures, specifically micropores and structures like nodules. So let's take a closer look at these two key features to understand their role in mineralization. First, our review of the heavily shady basalt CT images reveals that these nodules are prevalent across the entire heavily shady basalt, often appearing in massive cluster, as seen here. And it is crucial to note that they are not just isolated solid lumps. Instead, they are integrated with a network of microfractures and micropores. And you can see how the sub 60 micrometer micropore space surrounds these nodules, forming a highly accessible architecture for fluid flow. Furthermore, our geochemical analysis of nodules reveal that they are highly enriched in iron and magnesium, and we found that these nodules possess a highly amorphous character, which contributes to their highly reactive nature. And yeah, the fact that these reactive nodules with micropore network are distributed throughout the heavily shady basalt and indicates that this formation provides highly favorable conditions for CO2 mineralization. And next, let's take a closer look at the overall pore structures with this basalt. And as you can see, we conducted pore size distribution analysis for both heavily shady and Jeju basalt. And the results show that the pore size in this basalt span a very wide range with a multimodal distribution due to the presence of these large vesicles. What is particularly noteworthy here is that the significant contribution of the micropore scale domain, pores smaller than 60 micrometers. And in the heavily shady basalt, these micropores account for an average of 31% of the total pore volume, while in the Jeju basalt, they contribute a substantial 45%. And these findings clearly demonstrate that micropores are not just minor features. They constitute a substantial fraction of total pore space in basalt, confirming that the micropore network is a critical structural property that cannot be overlooked when evaluating mineralization. Then how do these micropores influence the fluid transport and reactive surface area, which are two critical factors for CO2 mineralization? Then let's first look at the results for permeability, which represents the transport characteristics. To begin, let me introduce the method. And we randomly extracted 1.5 cubic millimeter subvolumes from the 3D pore structures of both heavily shady and Jeju basalts, across both low and high resolutions. For each of these subvolumes, we calculated and plotted the porosity, permeability, and surface area to observe their correlations. And as you can see, at the low resolution, the data points follow the conventional Kosenik-Harman trend, which is a standard model for defining the relationship between porosity and permeability. However, once we capture the micropores through the high resolution imaging, this relationship completely collapses. There is no longer a specific correlation between porosity and permeability. And despite having nearly identical effective porosities, the permeability varies by as much as 5 orders of magnitude due to the influence of the micropores. And we observe this same phenomenon in the Jeju basalt as well. And the impact of these micropores is equally evident in our surface area results. As shown in the plots at the low resolution, the surface area increases with porosity. However, this correlation disappears in the high resolution data. And the surface area captured at the high resolution is between 6.5 5 times and 51 times higher than the low resolution estimates, despite having nearly identical porosity levels. And we observed a nearly identical trend in the accessible surface area, which represents the actual pore surfaces available for fluid flow. And furthermore, we found that the hilly shady basalts consistently exhibits a larger surface area compared to the Jeju basalt, and this difference is primarily due to the greater surface roughness of the hilly shady basalt samples. And we attribute this increased roughness to the presence of the nodal structures I described earlier, which significantly expands the reactive surface. And yeah, these findings lead us to a fundamental question. So how do these microstructural structural influences ultimately govern the CO2 mineralization potential? In specific, how does the synergy between the transport and reaction, which are dictated by the microstructures, determine the CO2 mineralization potential? To answer this, we developed a new framework, the Reactive Mineralization Potential Index, RMPI. And yeah, as shown here, RMPI is composed of 3 essential terms. First, the reactive surface availability, which represents the geometric capacity of the rock. And second, the reactive surface supply, which accounts for rate and efficiency of fluid renewal, which is the fuel for the reaction. And third, intrinsic reactivity derived from the rock's mineral composition. And yeah, this mathematical structure is analogous to the mass transfer coefficients formula, which is commonly used in the surface reaction kinetics. And yeah, and the most distinctive feature of this index is that its primary physical terms are derived directly from the high resolution imaging, capturing the hidden physics from the microstructures of the rock. So yeah, moving on, let me explain in more detail how we determined each of these terms. First, reactive surface availability represents the accessible surface area extracted from the multi-scale X-ray CT imaging images. And yeah, for the final index, we use a normalized value obtained by dividing the raw area by the specific bulk volume normalized reference value. And the second term, surface supply efficiency is defined as the average fluid velocity within the pore wall adjacent zone, the PWZ. And this zone represents the critical region where the actual mineralization reaction occurs at the rock fluid interface. And physically, this term captures the rate and efficiency of the fluid renewal, which provides the essential reactants for mineralization. And yeah, this is very important, vital, because if the fluid velocity near the surface is too low, the area becomes locally saturated, leading to a significant drop in reaction rates. Therefore, this parameter can be understood as the fluid transport activation in the vicinity of the reactive surface. And in the same way, this term is normalized by a characteristic Darcy scale velocity predicted for an idealized homogeneous medium. Finally, the intrinsic reactivity represents the rock's chemical potential, and we calculated the cumulative dissolution rate using the geochemical batch modeling for Halogene and Jeju basalt under the reservoir conditions, which were based on the specific mineral composition from the geochemical analysis. And we selected the dissolution rates as our proxy because the supply of divalent cations is the rate limiting step that governs carbonate precipitations. And since these cations are released during the matrix breakdown, dissolution kinetics can indicate the mineralization potential. And yeah, in the same way, values were normalized against the basaltic glass dissolution data for consistency from the previous study. And yeah, by integrating this reactivity with our capacity and transport terms, we establish a unified RMPI for a comprehensive quantitative evaluation. Now, yeah, let's see the result of our RMPI calculations. So in these plots, we have the normalized RMPI on the y-axis plotted against its two primary physical components on the x-axis. As you can clearly see in the left plot, RMPI is primarily governed by V, the activation, and this suggests that mineralization potential is determined not just by the mere abundance of surfaces, but by how effectively those surfaces are activated. In contrast, as shown in the right plot, the accessible surface area does not exhibit a single distinct correlation with RMPI. However, it is important to note that when comparable transport activation is achieved, RMPI increases systematically with increasing surface area. And this indicates that the capacity, accessible surface area, can act as a secondary but significant control. Finally, we observed a critical difference in imaging resolution. Our high-resolution data are distributed across a very wide range, reflecting their true pore scale variability. However, the low-resolution results collapse into a narrow cluster, which implies that the complex and multi-scale microstructures have been averaged out and masked at the coarser scales. And this leads us to a critical question. And what exactly do we lose when we rely on just low-resolution imagery for characterization? And to answer this, we quantify the difference between high and low resolution as a resolution-induced bias. And in this context, a bias greater than 0 indicates the underestimation at the low resolution, while a value below 0 signifies systematic overestimation at the low resolution. And as shown in the left plot, surface area tends to be underestimated at the low resolution. In contrast, V, the activation, is systematically overestimated, meaning that the coarser images, low resolution images, wrongly suggest much more efficient fluid transport than actually exists at the pore scales. Furthermore, we evaluated the bias against the micropore volume fraction. And as you can see, the degree of overestimation for mineralization potential increases as the rock structures become micropore rich. And this trend becomes particularly pronounced once the micropore fraction exceeds here, 0.3. And considering that both Helishady and Jeju basalts consist of more than 30% micropores, these results demonstrate that low to mid resolution analysis cannot reliably assess the true mineralization potential. Next, we investigate then how actual mineralization potential is distributed within the pore space. And to visualize this, we generated an RMPI map based on the micropore fraction and activity, and this map reveals several critical features of mineralization potential. First, the distribution of RMPI is highly non-uniform and polarized. Our analysis show a clear hotspot dominance in that the top of 24% of subvolumes account for approximately 90% of the total RMPI potential. And this indicates that CO2 mineralization is not spatially averaged phenomenon, but is instead governed by a few highly active hotspot regions. Second, we observe a significant lithology-dependent contrast. And as indicated by on open circles on the map, all the top ranked RMPI domains belong to the Helishady basalt. And this suggests that Helishady inherently possess a structurally superior capacity for mineralization compared to the Jeju basalt. Finally, the map confirms that the primary driver of this potential is the V, the surface activation, rather than simple surface area. And high RMPI domains occur only when a certain transport threshold is met, meaning that how effectively a surface is activated matters more than the total quantity of surface available. And yeah, then we examined what these hotspot regions actually look like in terms of their physical architecture. So our analysis reveals that domains with the high RMPI values possess a complex multi-scale pore structures. And so in these regions, large flow channels or vesicles are densely interconnected with surrounding micropore networks, as you can see here. And that is, these hotspots represent the microenvironments where the transport activation and surface accessibility are jointly maximized. Also, as you can see in the high-resolution cross-sections of the heli-shady basalt, the nodule structures are strategically formed on the vesicular surfaces where the primary fluid flow occurs. And these nodules serve to extend the micropore network, significantly boosting the reactive surface area and contributing to the exceptionally high RMPI. And in contrast, interjeju basalt lacks this level of complex integration, and its highest RMPI domains exhibit relatively simpler pore layouts with less developed micropore extensions, which leading to a much more mineralization potential at lower compared to the heli-shady. And yeah, in conclusion, CO2 mineralization potential is not a function of simple pore volume or surface area. Instead, it is concentrated in domains where large transport active pores are combined with adjacent micropore networks, creating a synergistic environment for the mineralization. So yeah, takeaways. And using the high-resolution X-ray CT imaging, we demonstrated that micropores are extensively developed in both basalt types, despite their very contrasting geologic origins and characteristics. And importantly, these micropores are not just minor pore features. They act as a fundamental structural elements that simultaneously regulate the fluid transport and reactive surface accessibility within the rock. And yeah, as a result of our MPI analysis, we evaluating CO2 mineralization potential based just only low to mid resolution images can lead to distorted interpretations because the critical microstructure features are spatially averaged and their coupled transport reaction effects are lost. And the mineralization potential concentrates in domains where the transport activation and surface accessibility are jointly maximized. Yeah, the references, and I'd like to express my sincere thanks to colleagues and mentors supporting this research. And yeah, that's all, and thank you for your time and attention. I'll be happy to take any questions and comments.
All right, thank you, Hyunjeong, for the wonderful talk. And again, those of you who are watching on YouTube and have questions, please write your questions in the chat, and that will be delivered to Hyunjeong. And while the audience on YouTube are writing their question, I have some questions to you.
Mm-hmm.
First of all, do you have plans to do some experimentation to validate your work?
To be honest, yes, but I cannot say the details about the experiments now. But yeah, I have a plan to do some experiments to prove these results, such as like a dissolution of nodules or changes in porosity, permeability, etc.
Yeah, I'll be curious to see how that matches with what you have found.
Mm-hmm.
And my second question is you may have explained this and I missed totally during your presentation, but if we go back to slides where you talk about the reactive potential index and how you calculated that, I think it's somewhere around 18 or page. Yeah. So
Mm-hmm.
looking at this got me thinking that micropores would have very low porosity, permeability, and some may be isolated from the flow conduit. So I was wondering how in real system, how effectively will they participate in the reaction? Because I don't know if even if they're physically, first of all, they may be isolated, disconnected from the advective flow paths, and also the flow velocity in the micropores will be very low, meaning that the Peclet will be fairly low. So I don't know how the solutes will be supplied to the surfaces in the micropores. So can you comment on how will they be really be significant in real system when you were to induce CO2 mineralization compared to macropores?
So you mean that the effect of micropores of pores on real mineralization system compared to macropores? Can I understand? Is that correct?
Yes. So I think the actual surface area of micropores, I assume some are not accessible and some are accessible. So I don't know how real system, like real rocks, if you were to induce CO2 mineralization, and I don't know how realistically the micropores will be accessible to or available to for mineralization. So can you comment on that?
Actually, these calculations of fluid, this term, which is the same as the average fluid velocity, were calculated within the effective pore, even for the micropores. I mean, you can see that this image, these are the micropores, which are connected, which are connected, and in this, I mean, the whole calculations of RMPI and analysis did not involve the isolated pore. So we just consider the effective pore of the micropores like this. But actually, in real systems, I think the isolated micropore also can affect the in real mineralization, but in this research, they are not considered. So I'm not convinced that this my answer is proper to your question, but
Yeah, you did. Yeah, thank you. I don't see any questions so far, but just a quick question about the imaging. Your imaging domain is 4.5 centimeter, and I forgot how long you have imaged your core sample, but how long does it take to get that level of resolution? I know it could take some time.
Yes, that's true. And we for the high resolution images, we just use the synchrotron, and the field of view for this high resolution is like 4 millimeter of diameter and 2 millimeter of the height. But it's very small. And for all the quantitative analysis, our region of interest sub-volume domain is 1.5 cubic millimeters for each plot of data.
I see. And how long does it
how long?
take, for you to get that volume scanned?
Actually, you mean for the just scanning?
Yes.
It took like how can I say a very quite short times, but it needs quite long times for just taking this high resolution images. I mean the setting of the this kind of setting. It took very long time, but just for the taking the images of the high resolution images, that process took quite a short time, like 20 minutes or
I see.
30 minutes.
Yeah, I was just wondering how feasible it will be to see the dynamics of this process if you were to do some experimentation.
You mean the obtaining this kind of high resolution during the experiment?
Yes.
We can, as far as I know, we can set the kind of experimental setup at this synchrotron beamline, and we can take some images for the regular with regular time interval.
See.
Yeah, but it takes very very high cost.
Yeah.
But we can take the
I see.
images of dynamic image changes by the obtaining images.
Yeah. Okay. Thank you. I don't think I see any questions in the chat. For the interest of time, I think we have to move on and finish our session. So thank you again, Hyunjeong, for your nice talk, and I look forward to seeing the future work, follow-up work from what you presented today. Hopefully, we'll be able to invite you again in the future. And okay. So thank you everyone for joining in, and this was the first time that we invite speakers directly from Korean Institute, and we hope to have more opportunity to host researchers not only in South Korea but around the globe to enhance diversity in our community and encourage dynamic networking and collaboration across the globe. Speaking of which, we have next month in March, we have a new set of speakers from Europe. Nathan from France and Carol from Poland will present their research on Pulse media. So please stay tuned. And Pulse media Tea Time Talk are composed of early career researchers who are working on also Pulse media research. And if you are interested in presenting your exciting work on our platform, please shoot us an email with your interest, or if you know someone who is doing really cool work and would like to have their work presented in our platform, please send us an email at the address shown here. And again, thank you all for joining us today, and we'll see you next time. Bye-bye.